Far beyond the familiar glow of our Milky Way lies another galaxy, Triangulum, a spiral beauty just under 3 million light-years away. A close neighbor in our cosmic neighborhood, the Triangulum galaxy holds secrets of stars, nebulae, and the vast expanses of the universe waiting to be explored. Tonight, we embark on a gentle journey through this distant galaxy, embracing the quiet beauty of its stars, dust, and mysteries. In the constellation of Triangulum, visible to the naked eye on the darkest nights, this galaxy has captivated astronomers for centuries. Known to scientists as Messier 33, or simply M33, it stands as the third largest galaxy in our local group of galaxies. While our own Milky Way and the mighty Andromeda galaxy dominate our cosmic neighborhood, Triangulum offers its own unique charm and wonder. As we begin this peaceful voyage through space and time, imagine yourself drifting slowly through the cosmic void, approaching this magnificent spiral galaxy. The darkness of space surrounds you, punctuated only by the gentle glow of distant stars and the soft, ethereal light of Triangulum itself. Here, in the quiet vastness of the universe, we find a place of profound beauty and mystery. The Triangulum galaxy spans roughly 60,000 light-years across, making it smaller than our own Milky Way, but no less remarkable. Its spiral arms sweep gracefully through space, adorned with brilliant star-forming regions and colorful nebulae that paint the cosmic canvas with hues of red, blue, and gold. These arms contain billions of stars, each with its own story to tell, its own journey through the cosmos. What makes Triangulum truly special is its active star formation. Unlike some galaxies that have grown quiet with age, Triangulum continues to birth new stars at a remarkable rate. The galaxy pulses with the energy of creation as massive clouds of gas and dust collapse under their own gravity to form the next generation of stellar lights. This ongoing process of stellar birth gives Triangulum a youthful vibrancy that we can observe even across the vast distances of space. As we prepare to explore this distant world, we carry with us the curiosity and wonder that drives all human exploration. Though we may never physically travel to Triangulum, our minds and imaginations can journey there tonight, guided by the light of knowledge and the peaceful rhythm of cosmic discovery. Let us begin our gentle voyage into the heart of this magnificent galaxy, where stars dance in their eternal ballet, and the universe reveals its most beautiful secrets. The journey ahead will take us through spiral arms filled with stellar nurseries, past ancient stars that have watched over this galaxy for billions of years, and into the mysterious regions where dark matter shapes the very structure of space itself. We will witness the birth of stars, the death of giants, and the endless cycle of creation that keeps the universe alive with light and possibility. So settle in, relax, and let your mind drift among the stars of Triangulum. In this place of cosmic tranquility, we find not only the beauty of distant worlds, but also a deeper connection to the vast universe that surrounds us all. The Triangulum galaxy awaits, ready to share its secrets with those who take the time to listen to the quiet whispers of the cosmos. The story of Triangulum begins long before human eyes first glimpsed its faint glow in the night sky. This galaxy has been spinning through space for over 10 billion years, quietly forming stars and evolving in the darkness between the larger galaxies of our local group. Its discovery by human astronomers represents just the tiniest fraction of its cosmic lifetime. Yet that moment of recognition opened a window into understanding one of our closest galactic neighbors. Charles Messier, the French astronomer who catalogued many celestial objects in the 1700s, first recorded Triangulum as the 33rd entry in his famous catalogue. He observed it through his telescope on a clear night in August of 1764. noting its fuzzy, nebulous appearance. At that time, astronomers had no idea they were looking at an entire galaxy filled with billions of stars. To them, it appeared as merely another mysterious cloud in the heavens, one of many enigmatic objects that populated the night sky. It would be more than a century before astronomers realized the true nature of these spiral nebulae. In the 1920s, Edwin Hubble used the powerful Mount Wilson telescope to resolve individual stars within Triangulum and other similar objects. This groundbreaking discovery revealed that these were not nearby gas clouds, but entire galaxies, each containing billions of stars and existing at tremendous distances from our own Milky Way. The universe suddenly became a much larger and more magnificent place. Today, we know that Triangulum sits approximately 2.7 million light-years away from Earth. To put this distance in perspective, if you could travel at the speed of light, it would take you 2,700,000 years to reach this galaxy. The light we see from Triangulum tonight began its journey toward us before modern humans had even evolved on Earth. We are literally looking back in time, witnessing the galaxy as it existed in the distant past. The Triangulum galaxy belongs to what astronomers call the local group, a collection of more than 50 galaxies bound together by gravity. This cosmic neighborhood spans about 10 million light-years across and contains 3 major spiral galaxies. The Andromeda Galaxy, also known as M31, is the largest member of our group. Our own Milky Way ranks as the second largest, while Triangulum holds the distinction of being the 3rd largest galaxy in our local cosmic family. What makes Triangulum particularly fascinating is its structure and composition. Unlike some galaxies that have evolved into smooth, elliptical shapes, Triangulum has maintained its beautiful spiral form. 2 prominent spiral arms sweep out from its central region, creating the classic pinwheel pattern that makes spiral galaxies so visually striking. These arms are not rigid structures, but rather density waves that move through the galaxy like ripples on a cosmic pond. The galaxy measures roughly 60,000 light-years in diameter, making it significantly smaller than both the Milky Way and Andromeda. However, this smaller size does not diminish its importance or beauty. In many ways, Triangulum offers astronomers a perfect laboratory for studying galactic evolution and star formation. Its face on orientation, as viewed from Earth, provides us with an excellent view of its spiral structure and the various regions where new stars are being born. Within this cosmic island, astronomers estimate that Triangulum contains somewhere between 10 billion and 40 billion stars. Each of these stars represents a sun, potentially warming planets and supporting the chemical processes that might lead to life. The sheer number of stars in Triangulum is almost impossible to comprehend. If you could count 1 star per second, it would take you over 1,000 years just to count to 1 billion, and Triangulum contains many times that number. The galaxy rotates slowly through space, completing 1 full rotation, approximately every 200 million years. This rotation is not uniform across the galaxy. Stars closer to the center orbit faster than those in the outer regions, creating the differential rotation that helps maintain the spiral arm structure. As the galaxy spins, it carries with it vast clouds of gas and dust, the raw materials from which new stars will eventually form. One of the most remarkable features of Triangulum is its ongoing star formation activity. While many galaxies have exhausted their star-forming materials and grown quiet with age, Triangulum continues to produce new stars at a vigorous rate. Astronomers can observe bright regions throughout the galaxy where massive, young stars illuminate the surrounding gas clouds, creating the colorful nebulae that give the galaxy much of its visual appeal. The gravitational influence of Triangulum extends far beyond its visible boundaries. Like all galaxies, it is surrounded by an enormous halo of dark matter, an invisible substance that comprises the majority of the galaxy's total mass. This dark matter halo helps bind the galaxy together and influences the motion of nearby smaller galaxies and star clusters. As we continue our journey through Triangulum, we will explore each of these aspects in greater detail. We will drift through the star-forming regions where new suns are born, examine the ancient stars that populate the galaxy's central regions, and investigate the mysterious dark matter that shapes the galaxy's structure. The Triangulum galaxy offers us a window into the fundamental processes that govern all galaxies, from the smallest dwarf galaxies to the largest elliptical giants. The history of Triangulum stretches back to the very early universe, when the first galaxies were beginning to form from primordial clouds of hydrogen and helium. In those ancient times, roughly 13 billion years ago, the universe was a very different place. There were no heavy elements like carbon or oxygen, no rocky planets, and no complex chemistry that could support life as we know it. Yet it was during this epoch that the seeds of Triangulum were planted. Through the slow accumulation of matter guided by the invisible hand of a dark matter, what would eventually become the Triangulum galaxy began to take shape. Small clumps of gas and the universe's first stars gradually merged and grew, forming larger and larger structures. This process, known as hierarchical assembly, continues today as Triangulum occasionally captures smaller satellite galaxies and incorporates their stars and gas into its own structure. The galaxy's spiral structure tells a story of cosmic evolution that spans billions of years. Unlike the chaotic, irregular galaxies that dominated the early universe, Triangulum has evolved into a mature spiral galaxy with well-defined arms and a central bulge. This transformation required time, patience, and the right conditions. The galaxy needed to accumulate enough matter to sustain ongoing star formation while avoiding major collisions that might have disrupted its delicate spiral pattern. Triangulum's position in the local group has played a crucial role in its development. Sitting at a comfortable distance from the larger Andromeda and Milky Way galaxies, it has avoided the gravitational disruptions that might have torn apart a galaxy in a more crowded cosmic neighborhood. This relative isolation has allowed Triangulum to maintain its star-forming capabilities and continue evolving at its own pace. The galaxy's metallicity, or abundance of heavy elements, provides clues about its star formation history. Early generations of stars in Triangulum were composed almost entirely of hydrogen and helium, the primordial elements left over from the Big Bang. As these massive stars lived out their brief lives and exploded as supernovae, they scattered heavier elements throughout the galaxy. Each subsequent generation of stars incorporated these elements, gradually enriching the galaxy's chemical composition. Today, Triangulum contains regions with varying levels of heavy element abundance. The central areas, where star formation began earliest, tend to be more metal-rich than the outer regions. This chemical gradient tells the story of how star formation has proceeded from the inside out, with newer stars forming in the less processed gas of the galaxy's outskirts. The galaxy's stellar population reveals itself in the colors and brightness of its different regions. The central bulge glows with a warm yellowish light, characteristic of older, cooler stars. These ancient suns have been shining for billions of years, some dating back to the galaxy's earliest epochs of star formation. In contrast, the spiral arms blaze with the brilliant blue-white light of young, massive stars that have formed within the last few million years. Triangulum's rotation curve, which describes how fast stars orbit at different distances from the galactic center, provides evidence for the presence of dark matter. If the galaxy contained only the visible matter we can observe, stars in the outer regions would orbit much more slowly than they actually do. The fact that these outer stars maintain relatively high orbital velocities indicates that they are influenced by the gravitational pull of unseen matter extending far beyond the galaxy's visible boundaries. The galaxy's magnetic field, though invisible to our eyes, plays an important role in shaping its structure and evolution. These magnetic fields help regulate star formation by influencing how gas clouds collapse and fragment. They also channel the flow of charged particles throughout the galaxy, creating the conditions necessary for the complex chemistry that occurs in stellar nurseries. Triangulum's interaction with its environment continues to shape its evolution. The galaxy experiences tidal forces from its larger neighbors, Andromeda and the Milky Way, which can trigger episodes of enhanced star formation. These gravitational interactions also influence the galaxy's overall trajectory through space, slowly altering its orbit within the local group. The study of Triangulum has contributed significantly to our understanding of galaxy formation and evolution. Because of its proximity and favorable orientation, astronomers can observe individual stars, star clusters, and nebulae within the galaxy in remarkable detail. This level of observation is impossible for more distant galaxies, making Triangulum an invaluable laboratory for testing theories about how galaxies develop and change over cosmic time. As we prepare to journey deeper into Triangulum, we carry with us this knowledge of its cosmic history and structure. The galaxy we are about to explore is not a static object, but a dynamic, evolving system that has been shaped by billions of years of cosmic evolution. Each star, each nebula, each spiral arm tells part of the story of how matter and energy have organized themselves into the beautiful structures we observe today. Now that we have met the Triangulum galaxy and understand its place in the cosmic order, let us step closer and drift into its spiral arms, where stars are born and the fabric of space reveals itself in the soft glow of nebulae. Our journey into the heart of this magnificent galaxy is about to begin, taking us to places where the universe writes its most beautiful stories in light and shadow. At the heart of every galaxy lies its most ancient and mysterious region, and Triangulum is no exception. As we drift toward the galactic center, we enter a realm where time seems to slow, and the very fabric of space bears witness to billions of years of cosmic history. The central bulge of Triangulum glows with a warm golden light, a testament to the ancient stars that have called this region home since the galaxy's earliest days. The galactic core of Triangulum differs significantly from the dramatic, highly active centers found in larger galaxies. Here, we find a relatively peaceful central region, lacking the violent outbursts and intense radiation that characterize the supermassive black holes at the hearts of bigger galactic systems. This gentler nature makes Triangulum's core a perfect place for quiet contemplation of the universe's deeper mysteries. Unlike the Milky Way or Andromeda, which harbor supermassive black holes containing millions or billions of times the mass of our Sun, Triangulum's central black hole remains modest in comparison. Astronomers estimate that if such a black hole exists at Triangulum's heart, it likely contains only a few thousand times the mass of our Sun. This relatively small central mass contributes to the galaxy's peaceful demeanor and allows us to observe stellar motions and interactions that might be overwhelmed by more violent gravitational forces in larger systems. The stars that populate Triangulum's central bulge tell the story of the galaxy's earliest epochs. These ancient suns formed when the universe was much younger, when the first generations of stars were beginning to enrich the cosmos with heavy elements. Many of these central stars are red giants and red supergiants, evolved stars that have swollen to enormous sizes as they near the end of their stellar lives. Their cool surfaces glow with a ruddy light that gives the galactic center its characteristic warm appearance. As we move through this central region, we encounter star clusters that have survived for billions of years. These globular clusters, spherical collections of hundreds of thousands of stars, orbit the galactic center like ancient satellites. Each cluster represents a fossil remnant of the galaxy's early star formation history, preserving within its stellar population the chemical signatures of the primordial universe. The dynamics of the galactic core reveal themselves through the orbital motions of stars around the central region. Unlike the organized rotation of the spiral arms, stellar orbits in the bulge follow more elliptical and chaotic paths. Some stars plunge deep into the central regions before swinging back out to the edges of the bulge, while others maintain more circular orbits at various distances from the galactic center. This complex orbital dance creates a three-dimensional structure that gives the central bulge its distinctive shape. The interstellar medium in Triangulum's core consists largely of hot, tenuous gas that has been heated and ionized by the radiation from ancient stars. This gas glows faintly in the infrared portion of the electromagnetic spectrum, creating a subtle backdrop against which the older stellar population stands out. Dust grains, forged in the atmospheres of dying stars, add their own contribution to the central region's appearance, creating dark lanes and patches that thread through the stellar field. Gravitational interactions between stars in the dense central region occasionally produce spectacular stellar encounters. When two stars pass close to each other, their gravitational fields can alter their orbits, sometimes flinging one star to the outer reaches of the galaxy, while the other settles into a tighter orbit around the galactic center. These encounters, while rare, help redistribute energy throughout the central stellar population and contribute to the long-term evolution of the galactic core. The central region of Triangulum also hosts a population of intermediate-age stars, formed during periods when infalling gas from the spiral arms triggered episodes of star formation in the bulge. These stars, while not as ancient as the original bulge population, are still considerably older than the young stars currently forming in the galaxy's outer regions. They provide a bridge between the ancient and modern epochs of Triangulum's evolution. Unlike the star-forming regions of the spiral arms, the galactic core of Triangulum has largely exhausted its supply of star-forming material. The intense radiation from the central stellar population has heated and dispersed much of the gas that might otherwise collapse to form new stars. This creates a stable environment where the existing stellar population can evolve undisturbed by the violent processes associated with ongoing star formation. The magnetic field structure in Triangulum's core reflects the complex motions of the stellar population and the hot gas that permeates the region. These magnetic fields, while much weaker than those found in the star-forming regions of the spiral arms, still play a role in shaping the flow of charged particles and the overall structure of the interstellar medium in the central region. As we observe the galactic core from our cosmic vantage point, we can appreciate the subtle beauty of this ancient region. The steady glow of billions of old stars creates a serene environment, free from the dramatic fireworks of star formation that characterize other parts of the galaxy. Here, in the heart of Triangulum, we find a place where the universe's past is preserved in the gentle light of stars that have witnessed the galaxy's entire evolutionary history. The central region also serves as a gravitational anchor for the entire galaxy. The combined mass of all the stars in the bulge, along with the dark matter halo that surrounds the galaxy, provides the gravitational foundation that holds the spiral structure together. Without this central mass concentration, the beautiful spiral arms we observe would quickly dissolve into a chaotic distribution of stars and gas. Temperature variations throughout the galactic core create subtle differences in stellar populations at different distances from the center. Stars closer to the galactic center tend to be more metal-rich, reflecting their formation from gas that had been enriched by multiple generations of stellar nucleosynthesis. Those farther out in the bulge often show lower heavy element abundances, indicating their formation from less processed material. The study of Triangulum's galactic core provides astronomers with insights into the formation and evolution of spiral galaxies in general. The relatively undisturbed nature of this central region allows researchers to observe stellar populations and dynamics that might be obscured or altered in more active galactic centers. This makes Triangulum's core an excellent laboratory for understanding how galactic bulges form and evolve over cosmic time. The formation of Triangulum's central bulge occurred through a complex process known as secular evolution. Unlike galaxy mergers that can create bulges through violent interactions, Triangulum's central region likely formed through the gradual inward migration of stars and gas from the galaxy's disk. Over billions of years, gravitational interactions and instabilities in the spiral structure have slowly fed material into the central region, building up the stellar population we observe today. Within the galactic core, we can observe the effects of stellar evolution on a grand scale. Many of the stars in this region have already completed their main sequence lifetimes and evolved into red giants or white dwarf stars. The red giants, with their extended atmospheres and cool surface temperatures, dominate the visual appearance of the central region. These evolved stars are slowly losing mass through stellar winds, enriching the interstellar medium with heavy elements that will eventually be incorporated into future generations of stars. The white dwarf stars that populate the central region represent the end stage of stellar evolution for stars similar to our Sun. These incredibly dense objects, containing roughly the mass of our Sun, compressed into a sphere the size of Earth, no longer undergo nuclear fusion in their cores. Instead, they slowly cool over billions of years, gradually fading from white-hot to red and eventually to black. The presence of these white dwarfs in Triangulum's core speaks to the great age of the stellar population in this region. Neutron stars, the collapsed cores of massive stars that exploded as supernovae, also inhabit the galactic core. These exotic objects, containing more mass than our Sun compressed into a sphere only 20 kilometers across, spin rapidly and emit beams of radiation that sweep across space like cosmic lighthouses. When these beams point toward Earth, we detect them as pulsars, providing us with precise timing signals that allow astronomers to study the structure and dynamics of the galactic core. The chemical composition of stars in Triangulum's central region reveals the history of stellar nucleosynthesis within the galaxy. Elements heavier than hydrogen and helium, which astronomers call metals, were forged in the cores of massive stars and dispersed through supernova explosions. The metal-rich stars in the galactic core formed from gas that had been enriched by many previous generations of stellar evolution, while the metal-poor stars represent some of the galaxy's earliest stellar inhabitants. Variable stars in the central region provide astronomers with tools for measuring distances and understanding stellar evolution. Cepheid variable stars, which pulsate with regular periods related to their intrinsic brightness, serve as cosmic distance markers. RR Lyrae variables, found primarily in the galaxy's globular clusters, help astronomers determine the age and metallicity of the oldest stellar populations. These stellar lighthouses allow us to probe the three-dimensional structure of the galactic core and trace its evolutionary history. The gravitational field in Triangulum's central region creates a complex environment for stellar orbits. Unlike the relatively circular orbits of stars in the galactic disk, stars in the bulge follow elongated, three-dimensional paths that can carry them far from the galactic plane. Some stars in the central region have highly eccentric orbits that bring them close to the galactic center before flinging them out to the edges of the bulge. These orbital variations contribute to the spherical shape of the central region and help maintain its structural stability over cosmic time. Gas dynamics in the galactic core differ significantly from those in the spiral arms. The hot, ionized gas that permeates the central region has been heated by stellar radiation and supernova explosions to temperatures of millions of degrees. This hot gas is too energetic to collapse and form new stars, instead flowing outward from the central region in gentle galactic winds. These winds carry heavy elements produced by stellar nucleosynthesis into the galaxy's halo, enriching the circumgalactic medium with the products of stellar evolution. The central region of Triangulum also hosts a population of binary star systems, where two stars orbit around their common center of mass. These binary systems can produce spectacular phenomena when one star transfers matter to its companion. If one member of the binary is a white dwarf, the transferred material can accumulate on its surface until it ignites in a thermonuclear explosion, creating a nova that briefly outshines all other stars in the galaxy. If the white dwarf accumulates enough matter, it can explode completely as a Type 1 supernova, one of the most powerful explosions in the universe. The dark matter distribution in the galactic core plays a crucial role in maintaining the structural integrity of the central region. Computer simulations suggest that the dark matter density peaks toward the galactic center, creating a deep gravitational well that helps bind the stellar population together. This invisible scaffolding of dark matter provides the gravitational framework that allows the complex orbital dynamics of the central region to persist over billions of years. Stellar streams and tidal tails from disrupted star clusters occasionally pass through the galactic core, adding their stars to the central population. These streams, created when the tidal forces of the galaxy overcome the gravitational binding of small stellar systems, provide a mechanism for the ongoing accretion of stars into the central region. The gradual incorporation of these disrupted systems contributes to the growth and evolution of the galactic bulge over cosmic time. The study of stellar kinematics in Triangulum's core reveals the presence of multiple stellar populations with different velocity dispersions and orbital characteristics. Some stars follow relatively ordered orbits that reflect the galaxy's rotation, while others exhibit more random motions characteristic of a pressure-supported system. This kinematic complexity suggests that the central region formed through multiple episodes of star formation and accretion, each leaving its own signature in the stellar velocity distribution. As we contemplate the galactic core of Triangulum, we find ourselves in the presence of cosmic history made manifest. The ancient stars that populate this region have witnessed the entire evolutionary history of the galaxy, from its earliest epochs of star formation to the present day. Their steady glow provides a sense of permanence and continuity in a universe that is constantly changing and evolving. The central region serves as a repository of the galaxy's memory, preserving in its stellar populations the chemical signatures of past episodes of star formation and stellar evolution. Each star carries within its atmosphere the record of the nuclear processes that created the heavy elements we observe today. By studying these stellar fossils, astronomers can reconstruct the history of chemical enrichment in the galaxy and understand how the raw materials for planets and life were gradually assembled over cosmic time. At the core of every galaxy lies its heart, a region of ancient stars and hidden forces. But as we move outward from this peaceful center, the stars and nebulae of the spiral arms come into view, vibrant and full of life. Our journey now takes us from the quiet contemplation of the galactic core to the dynamic star-forming regions where the galaxy's future is being written in the birth of new stars. As we drift outward from the ancient heart of Triangulum, we enter a realm of cosmic creativity, where the universe demonstrates its most remarkable talent, the birth of stars. The spiral arms of Triangulum sweep gracefully through space like cosmic rivers of light, carrying within their flowing structure the raw materials and conditions necessary for stellar formation. Here, in these magnificent spiral patterns, we witness the ongoing creation of new suns that will illuminate the galaxy for billions of years to come. The spiral arms of Triangulum are not solid structures, but rather density waves that propagate through the galactic disk like ripples on a cosmic pond. These waves compress the gas and dust as they pass, creating the conditions necessary for gravitational collapse and star formation. The arms themselves rotate more slowly than the individual stars, allowing stellar material to flow into and out of the spiral pattern as the galaxy evolves. This dynamic process ensures that the spiral structure persists over cosmic time, while continuously recycling material through cycles of stellar birth and death. As we enter the first major spiral arm, we immediately notice the dramatic change in our cosmic environment. Gone is the warm, steady glow of the ancient central region, replaced by the brilliant blue-white light of young, massive stars that have formed within the last few million years. These stellar giants burn their nuclear fuel at prodigious rates, shining with luminosities thousands of times greater than our Sun. Their intense radiation ionizes the surrounding gas clouds, creating vast regions of glowing plasma that paint the spiral arms with vibrant colors. The process of star formation begins in the cold, dark molecular clouds that drift through the spiral arms. These clouds, composed primarily of hydrogen molecules with trace amounts of heavier elements and dust grains, can remain stable for millions of years until something triggers their gravitational collapse. The passage of a spiral density wave often provides this trigger, compressing the cloud and causing dense regions within it to contract under their own gravity. Within these collapsing regions, known as stellar nurseries, the temperature and pressure gradually increase as gravity pulls more and more material toward the center. When the core temperature reaches about 10 million degrees Celsius, nuclear fusion ignites and a new star is born. The exact mass of the resulting star depends on how much material was available in the original cloud and how efficiently it could be gathered during the collapse process. The most massive stars that form in Triangulum's spiral arms are true stellar giants, containing 20, 50, or even 100 times the mass of our Sun. These massive stars live brief but spectacular lives, burning through their nuclear fuel in just a few million years before exploding as supernovae. During their short lifetimes, they pump enormous amounts of energy into their surroundings, heating and ionizing vast volumes of gas and triggering the formation of additional stars in nearby molecular clouds. The stellar associations that populate the spiral arms contain stars of all masses, from the massive blue giants down to tiny red dwarf stars that will continue shining for trillions of years. Young star clusters, gravitationally bound groups of stars that formed from the same molecular cloud, drift through the spiral arms like cosmic families. These clusters gradually disperse over time as gravitational interactions with other stars and gas clouds slowly tear them apart, spreading their member stars throughout the galactic disk. The interstellar medium within the spiral arms presents a complex tapestry of gas at different temperatures and densities. Hot, ionized gas heated by massive stars glows brightly in the visible portion of the electromagnetic spectrum, creating the colorful emission nebulae that make the spiral arms so visually striking. Cooler gas, shielded from stellar radiation by dust grains, remains neutral and can be detected through radio observations of hydrogen atoms and molecules. Dust plays a crucial role in the star formation process within the spiral arms. These microscopic grains, composed of silicates, carbon compounds, and ice, absorb starlight and re-emit it in the infrared portion of the spectrum. The dust also serves as a catalyst for chemical reactions that create complex molecules in the cold depths of molecular clouds. Without dust, the chemistry necessary for star and planet formation would be severely impaired. The magnetic fields that thread through the spiral arms help regulate the star formation process by providing additional support against gravitational collapse. These fields, though incredibly weak by terrestrial standards, can significantly influence the dynamics of the tenuous interstellar gas. The interaction between magnetic fields, turbulence, and gravity creates a delicate balance that determines when and where new stars will form within the spiral structure. Supernova explosions within the spiral arms create vast bubbles of hot gas that can trigger star formation in surrounding molecular clouds, while simultaneously disrupting ongoing stellar birth in nearby regions. These stellar explosions inject enormous amounts of energy into the interstellar medium, heating gas to temperatures of millions of degrees and creating shockwaves that propagate through the spiral arms. The heavy elements forged in the cores of massive stars are scattered by these explosions, enriching the interstellar medium with the raw materials necessary for the formation of rocky planets. The spiral arms of Triangulum host some of the most spectacular star-forming regions known to astronomy. These giant molecular cloud complexes can span hundreds of light years and contain enough material to form millions of stars. Within these regions, we find a hierarchy of structure, from the largest cloud complexes down to the individual dense cores where individual stars are born. The entire process, from the initial compression of a molecular cloud to the emergence of a fully formed stellar system, can take several million years. Young stellar objects within the spiral arms often exhibit dramatic variability as they settle into stable nuclear burning. These protostars are surrounded by disks of gas and dust from which planetary systems may eventually form. The strong stellar winds and radiation from nearby massive stars can sculpt these protoplanetary disks, influencing the eventual architecture of any planetary systems that develop. The spiral density waves that create the arm structure also influence the orbital motions of stars and gas clouds throughout the galactic disk. As material flows into a spiral arm, it experiences increased gravitational forces that can alter its trajectory and velocity. This process helps maintain the spiral pattern while also facilitating the mixing of material between different regions of the galaxy. Brown dwarfs, failed stars that never achieved sufficient mass to sustain nuclear fusion, are also products of the star formation process in the spiral arms. These objects, with masses between those of the largest planets and the smallest stars, glow dimly from the heat of their gravitational contraction. Though they contribute little light to the galaxy, brown dwarfs may be quite numerous and represent an important component of the galactic mass budget. The stellar initial mass function, which describes the relative numbers of stars formed at different masses, appears to be remarkably similar in different star-forming regions throughout Triangulum's spiral arms. This universality suggests that the fundamental physics of star formation operates in the same way throughout the galaxy, despite variations in local conditions such as gas density, temperature, and magnetic field strength. Stellar feedback, the energy and momentum injected into the interstellar medium by young stars, plays a crucial role in regulating star formation within the spiral arms. Massive stars not only heat and ionize their surroundings, but also drive powerful stellar winds that can clear away nearby gas and dust. This feedback can both trigger star formation in distant molecular clouds and suppress it in the immediate vicinity of the massive stars. As we journey through the spiral arms of Triangulum, we witness the universe's most fundamental creative process. Here, gravity, magnetism, and nuclear physics combine to transform cold, dark clouds of gas and dust into brilliant stars that will shine for billions of years. The spiral arms serve as cosmic assembly lines, continuously producing new generations of stars that carry forward the chemical heritage of their predecessors while adding their own contributions to the galaxy's ongoing evolution. The beauty of the spiral arms lies not only in their visual splendor, but also in the elegant physics that governs their structure and evolution. The density waves that create the spiral pattern represent a delicate balance between gravitational forces and the rotation of the galaxy. This balance has been maintained for billions of years, allowing Triangulum to preserve its spiral structure while continuously creating new stars and recycling stellar material through successive generations. As we drift through the spiral arms, we find ourselves in the birthplace of stars. The glowing nebulae around us are the factories of creation, where new stars are born and the cycle of life in the galaxy continues. Our journey now takes us deeper into these stellar nurseries, where we will explore the intricate processes that transform dark clouds of gas and dust into the brilliant beacons of light that illuminate the cosmos. Within the spiral arms of Triangulum, we encounter some of the most breathtaking and scientifically significant objects in the galaxy, the nebulae. These vast clouds of gas and dust serve as both the birthplaces and graveyards of stars, creating a cosmic cycle of death and rebirth that has continued for billions of years. As we drift through these ethereal structures, we witness the universe painting with light, using the fundamental forces of physics to create masterpieces of unimaginable beauty and scale. The nebulae of Triangulum come in many varieties, each telling its own story of stellar evolution and cosmic chemistry. Emission nebulae glow with the characteristic colors of ionized hydrogen, oxygen, and other elements, energized by the intense ultraviolet radiation from nearby young stars. These stellar nurseries appear as vast red, pink, and blue regions scattered throughout the spiral arms, their colors determined by the specific atoms and ions present in the gas and the energy of the radiation that excites them. Among the most spectacular emission nebulae in Triangulum is NGC 604, one of the largest and most luminous star-forming regions known in the local group of galaxies. This massive nebula spans nearly 1,500 light-years across and contains more than 200 of the hottest, most massive stars known to astronomy. The combined energy output of these stellar giants ionizes a volume of space larger than many entire galaxies, creating a beacon of star formation that can be observed across millions of light-years of intergalactic space. The process that creates these glowing nebulae begins when massive young stars emit intense ultraviolet radiation that strips electrons from hydrogen atoms in the surrounding gas. This ionization process creates a plasma of free electrons and protons that glows when the electrons recombine with the atomic nuclei. The characteristic red color of many emission nebulae comes from hydrogen atoms transitioning between specific energy levels, while other elements contribute their own distinctive spectral signatures to create the complex palette of colors we observe. Reflection. Nebulae present a different type of cosmic beauty, appearing as blue clouds that scatter the light from nearby stars without ionizing the gas. These nebulae are composed of dust grains that are similar in size to the wavelength of visible light, causing them to scatter blue light more efficiently than red light, much like the process that makes Earth's sky appear blue. The dust grains in reflection nebulae are often composed of silicates, carbon compounds, and ice mantles that formed in the atmospheres of dying stars and were subsequently dispersed into the interstellar medium. Dark nebulae, perhaps the most mysterious of all nebula types, appear as dark patches silhouetted against the brighter background of stars and glowing gas. These dense clouds of dust block the light from more distant objects, creating the appearance of holes in the stellar background. Far from being empty voids, dark nebulae are often the densest regions of the interstellar medium, containing the cold molecular gas from which the next generation of stars will eventually form. The Triangulum galaxy hosts numerous planetary nebulae, the beautiful death shrouds of stars similar to our Sun. When these moderate mass stars exhaust their nuclear fuel, they shed their outer layers in a series of gentle pulsations, creating expanding shells of ionized gas that glow with spectacular colors. The central white dwarf star, the hot, dense core left behind after the stellar envelope is ejected, provides the ultraviolet radiation necessary to ionize the expanding gas shell and create the nebula's characteristic glow. These planetary nebulae, despite their name having nothing to do with planets, represent one of the most important mechanisms for enriching the interstellar medium with heavy elements. During their final evolutionary phases, stars like our Sun dredge up carbon, nitrogen, and other elements from their interiors and disperse them into space through stellar winds and the eventual ejection of their outer layers. This process returns to the galaxy the products of stellar nucleosynthesis, making them available for incorporation into future generations of stars and planets. Supernova remnants create some of the most dramatic and energetic nebulae in Triangulum. When massive stars explode at the end of their lives, they blast their outer layers into space at velocities of thousands of kilometers per second, creating expanding shock waves that sweep up and heat the surrounding interstellar medium. These supernova remnants can remain visible for tens of thousands of years, gradually fading as they expand and cool. The shock waves from supernova explosions play a crucial role in triggering star formation in nearby molecular clouds. As the expanding blast wave encounters a dense cloud of gas and dust, it compresses the material and can initiate the gravitational collapse that leads to stellar birth. This process creates a feedback loop where the death of massive stars triggers the formation of new stellar generations, ensuring the continuation of the cosmic cycle of stellar evolution. Within the nebulae of Triangulum, we can observe the complex chemistry that occurs in the interstellar medium. The harsh radiation environment and extreme physical conditions present in these regions drive chemical reactions that would be impossible under terrestrial conditions. Water, ammonia, methanol, and even complex organic molecules have been detected in the dense cores of molecular clouds, suggesting that the building blocks of life may be common throughout the galaxy. The magnetic fields that permeate the nebulae play an important role in shaping their structure and evolution. These fields, though incredibly weak, can influence the motion of charged particles and the flow of ionized gas within the nebulae. The interaction between magnetic fields, stellar winds, and radiation pressure creates complex patterns of compression and rarefaction that give each nebula its unique morphology. Herbig-Haro objects, small patches of nebulosity associated with newly formed stars, provide direct evidence of the violent processes that accompany stellar birth. These objects form when high-velocity jets of gas, expelled by young stars, collide with the surrounding interstellar medium, creating shock waves that heat and ionize the gas. The study of Herbig-Haro objects has revealed important details about how young stars interact with their environment and how planetary systems might form in the chaotic conditions near stellar nurseries. The dust grains within Triangulum's nebulae serve as more than just light scattering and absorbing particles. These microscopic structures act as catalysts for chemical reactions and provide surfaces on which atoms and molecules can meet and combine. The formation of molecular hydrogen, the most abundant molecule in the universe, depends critically on reactions that occur on the surfaces of dust grains in the cold depths of molecular clouds. Wolf-Rayet stars, extremely hot and massive evolved stars, create some of the most spectacular nebulae in Triangulum through their powerful stellar winds. These stars, which have shed their outer hydrogen layers to reveal their hot helium and carbon-rich cores, drive winds with velocities exceeding 2,000 kilometers per second. When these winds collide with material ejected during earlier evolutionary phases, they create beautiful ring-shaped and bubble-shaped nebulae. The study of nebulae in Triangulum provides astronomers with laboratories for understanding fundamental astrophysical processes. The extreme conditions present in these objects, from the intense radiation fields near massive stars to the frigid environments in the cores of molecular clouds, allow researchers to test theories about atomic and molecular physics, fluid dynamics, and magnetohydrodynamics under conditions that cannot be replicated on Earth. Cometary globules, small dark nebulae with distinctive comet-like shapes, dot the landscape of Triangulum's star-forming regions. These objects form when dense molecular clouds are sculpted by the radiation and stellar winds from nearby massive stars. The intense stellar radiation evaporates material from one side of the cloud, creating a tail-like structure that points away from the ionizing star, while the denser core remains relatively protected from the destructive effects of stellar radiation. The temperature structure within Triangulum's nebulae reveals the complex energy balance between heating and cooling processes. Near massive stars, the gas can be heated to temperatures of tens of thousands of degrees by stellar radiation and shockwaves. In contrast, the dense cores of molecular clouds can cool to just a few degrees above absolute zero, creating some of the coldest naturally occurring environments in the universe. Photodissociation regions, where stellar ultraviolet radiation gradually breaks apart molecules in the outer layers of molecular clouds, create transition zones between the ionized gas of emission nebulae and the cold molecular material of stellar nurseries. These regions exhibit complex chemical gradients as molecules are destroyed and reformed under the influence of stellar radiation, creating a rich tapestry of atomic and molecular species. The life cycle of nebulae in Triangulum spans millions of years, from their formation in the aftermath of stellar death or in the compressed gas of spiral arms, through their role as stellar nurseries, to their eventual dispersal by stellar winds and supernova explosions. This continuous cycle of creation and destruction ensures that the galaxy remains vibrant and active, constantly recycling material through successive generations of stellar evolution. As we journey through the nebulae of Triangulum, we witness the universe's most fundamental creative processes at work. These cosmic clouds serve as both museums of stellar death and nurseries of stellar birth, preserving the chemical heritage of past generations while nurturing the stars that will illuminate the galaxy's future. The nebulae of Triangulum are not just places of beauty, they are the birthplaces of the future. Here, light and dust dance in an eternal cycle of creation and destruction, weaving the story of cosmic evolution in threads of glowing gas and stellar fire. As we continue our gentle journey through the Triangulum galaxy, we turn our attention to the individual stars that populate this cosmic island. Each star represents a unique story of nuclear fusion, gravitational balance, and stellar evolution, contributing its own voice to the grand symphony of galactic life. From the smallest red dwarf stars that will outlive the galaxy itself to the massive blue supergiants that burn brilliantly for just a few million years. Triangulum hosts an incredible diversity of stellar types that illuminate the many pathways of cosmic evolution. The stars of Triangulum span an enormous range of masses, from tiny brown dwarfs containing less than 8% the mass of our Sun, to massive hypergiants that may contain more than 100 times our Sun's mass. This stellar mass spectrum determines not only how bright each star appears, but also how long it will live, how it will evolve, and ultimately how it will die. The most massive stars live fast and die young, while the smallest stars burn their nuclear fuel so slowly that they can continue shining for trillions of years. Red dwarf stars, the most common type of star in Triangulum, represent the galaxy's most patient inhabitants. These small, cool stars contain between 8% and 40% the mass of our Sun and burn their hydrogen fuel so efficiently that they can maintain nuclear fusion for hundreds of billions of years. Their surfaces glow with a ruddy light at temperatures between 2,000 and 4,000 degrees Celsius, making them much cooler than our Sun. Despite their small size and low luminosity, red dwarfs may represent up to 75% of all stars in the galaxy. The longevity of red dwarf stars means that every red dwarf that has ever formed in Triangulum is still shining today. These ancient stars serve as fossil records of the galaxy's early star formation history, preserving in their atmospheres the chemical signatures of the primordial gas from which they formed. As Triangulum continues to evolve over cosmic time, red dwarf stars will eventually become the galaxy's only remaining stellar inhabitants, continuing to shine long after all other types of stars have exhausted their nuclear fuel. Yellow dwarf stars, like our own Sun, occupy a middle ground in the stellar mass spectrum. These stars, with masses between 80% and 1.2 times that of our Sun, maintain a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. This balance allows them to shine steadily for approximately 10 billion years, providing stable energy sources that could potentially support the development of life on orbiting planets. The surface temperature of yellow dwarf stars ranges from 5,000 to 6,000 degrees Celsius, giving them their characteristic warm, yellowish glow. During their main sequence lifetimes, these stars gradually increase in brightness as the helium ash from nuclear fusion accumulates in their cores. This slow evolution means that any planets orbiting yellow dwarf stars must adapt to changing conditions over geological timescales. Orange dwarf stars, slightly smaller and cooler than our Sun, may represent the most favorable stellar environments for the development of life. These stars, containing between half and 80% the mass of our Sun, burn their nuclear fuel even more slowly than yellow dwarfs, allowing them to maintain stable energy output for 20 to 30 billion years. Their cooler surface temperatures, ranging from 3,500 to 5,000 degrees Celsius, mean that their habitable zones, where liquid water could exist on planetary surfaces, lie closer to the star than in solar-type systems. The K-type orange dwarf stars in Triangulum are particularly interesting to astronomers searching for potentially habitable worlds. Their long main sequence lifetimes provide ample time for complex chemistry and biological evolution to occur on any orbiting planets. Additionally, these stars produce less harmful high-energy radiation than more massive stars, creating gentler environments for atmospheric retention and the preservation of liquid water. Blue giant stars represent the aristocrats of Triangulum's stellar population. These massive stars, containing between 10 and 50 times the mass of our Sun, burn their nuclear fuel at such prodigious rates that they can consume their entire hydrogen supply in just 10 to 100 million years. Their surface temperatures exceed 20,000 degrees Celsius, giving them their characteristic brilliant blue-white color and making them among the most luminous objects in the galaxy. The intense radiation from blue giant stars ionizes vast volumes of surrounding gas, creating the spectacular emission nebulae that make Triangulum's spiral arms so visually striking. These stellar powerhouses drive strong stellar winds that can reach velocities of several thousand kilometers per second, sculpting the interstellar medium and triggering star formation in nearby molecular clouds. Despite their brief lifetimes, blue giants play a crucial role in the chemical evolution of the galaxy. Red giant stars mark an important evolutionary phase for stars similar to our Sun. When these moderate mass stars exhaust the hydrogen fuel in their cores, they begin fusing helium while their outer layers expand and cool. This transformation causes the star's surface to become much cooler, around 3,000 degrees Celsius, while its radius increases by factors of 10 to 100. The result is a luminous red giant that can outshine its main sequence brightness despite its cooler surface temperature. The red giant phase represents a time of instability and change in stellar evolution. These stars often pulsate with periods ranging from days to years, causing their brightness to vary significantly over time. The pulsations are driven by complex interactions between the star's nuclear burning regions and its greatly expanded outer layers. Some red giants develop strong stellar winds that carry away significant portions of their mass, enriching the interstellar medium with heavy elements forged in their cores. White dwarf stars in Triangulum represent the final evolutionary stage for stars, with initial masses up to about 8 times that of our Sun. These incredibly dense objects contain roughly the mass of our Sun compressed into a sphere about the size of Earth. With surface temperatures initially reaching 100,000 degrees Celsius, white dwarfs slowly cool over billions of years, gradually fading from brilliant white to dim red, and eventually to cold black dwarf stars. The study of white dwarf stars in Triangulum provides important insights into stellar evolution and the age of the galaxy. Since white dwarfs cool at predictable rates, astronomers can use their temperatures and colors to estimate how long ago their progenitor stars died. The coolest white dwarfs in Triangulum help establish lower limits on the age of the galaxy's stellar population and provide clues about the early epochs of star formation. Neutron stars, though incredibly rare and difficult to observe directly, represent one of the most exotic forms of matter in the Triangulum galaxy. These stellar remnants form when massive stars, typically those with initial masses greater than 20 times our Sun, undergo core collapse during supernova explosions. The resulting neutron star contains more mass than our Sun compressed into a sphere only 20 kilometers in diameter, creating densities comparable to atomic nuclei. Some neutron stars in Triangulum manifest themselves as pulsars, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space like lighthouse beams, and when they point toward Earth, we detect regular pulses of radio waves, X-rays, or gamma rays. The precision of pulsar timing has made these objects invaluable tools for testing theories of gravity and studying the structure of space and time. Variable stars throughout Triangulum provide astronomers with powerful tools for measuring distances and understanding stellar physics. Cepheid variable stars, massive yellow supergiant stars that pulsate with periods ranging from 1 day to several months, serve as cosmic distance indicators because their pulsation periods are directly related to their intrinsic brightness. This period luminosity relationship allows astronomers to determine the distance to Triangulum and other nearby galaxies with remarkable precision. RR, Lyrae variable stars, found primarily in the galaxy's globular star clusters, represent another important class of stellar distance indicators. These old, low-mass stars pulsate with periods of less than 1 day, and all have roughly the same intrinsic brightness. The discovery of RR Lyrae stars in Triangulum's halo helps astronomers map the three-dimensional structure of the galaxy and understand its formation history. Binary star systems, where 2 stars orbit around their common center of mass, are remarkably common throughout Triangulum. Astronomers estimate that more than half of all stars exist in binary or multiple star systems. These gravitationally bound pairs can produce spectacular phenomena when the stars interact with each other, transferring mass and energy in complex ways that can dramatically alter their evolutionary paths. Close binary systems, where the 2 stars orbit within a few stellar radii of each other, can experience episodes of mass transfer when one star evolves to become a red giant. If the companion star is a white dwarf, the transferred material can accumulate on its surface until it ignites in a thermonuclear explosion, creating a nova that briefly outshines all other stars in the galaxy. In extreme cases, the white dwarf can accumulate enough mass to undergo complete nuclear detonation, producing a type Ia supernova. Contact binary systems, where 2 stars actually touch and share a common envelope, represent an even more extreme form of stellar interaction. These systems evolve rapidly as the 2 stars spiral closer together, eventually merging to form a single, more massive star. The merger process can trigger episodes of enhanced nuclear burning and mass ejection that temporarily increase the system's brightness. Stellar metallicity, the abundance of elements heavier than hydrogen and helium, varies significantly among the stars of Triangulum. The oldest stars, formed when the galaxy was young, contain very low abundances of heavy elements because they formed from primordial gas that had not yet been enriched by stellar nucleosynthesis. Younger stars show progressively higher metallicities as successive generations of stellar evolution have gradually increased the heavy element content of the interstellar medium. The metallicity gradient observed in Triangulum, with metal-rich stars concentrated toward the galactic center and metal-poor stars dominating the outer regions, reflects the inside-out nature of galactic chemical evolution. Star formation began earliest in the central regions, where the gas density was highest, and gradually spread outward as the galaxy evolved. This process created the chemical gradients we observe today, and provides important clues about how spiral galaxies form and evolve. Stellar rotation rates vary dramatically among different types of stars in Triangulum. Massive stars often rotate rapidly, with some approaching their breakup velocities, where centrifugal forces nearly overcome gravitational binding. This rapid rotation can affect stellar evolution by mixing nuclear processed material from the core to the surface and driving strong stellar winds. In contrast, older stars, like red giants, typically rotate much more slowly due to magnetic braking and tidal interactions with stellar companions. The stellar initial mass function, which describes the relative numbers of stars formed at different masses, appears to be remarkably universal throughout Triangulum. Observations of star-forming regions across the galaxy show that low-mass stars are much more common than high-mass stars, with the number of stars decreasing roughly as the inverse square of stellar mass. This universal pattern suggests that the fundamental physics of star formation operates similarly throughout the galaxy. Stellar magnetic fields play important roles in many aspects of stellar evolution and behavior. Young stars often possess strong magnetic fields that can channel the flow of infalling material during the star formation process and drive powerful stellar winds and jets. As stars age, their magnetic fields typically weaken, though some evolved stars can regenerate strong fields through dynamo processes in their convective outer layers. The study of stellar populations in Triangulum reveals the complex history of star formation throughout the galaxy's evolution. Population-wise stars, which include our Sun and most of the stars visible in the galactic disk, are relatively young and metal-rich. Population 2 stars, found primarily in the galactic halo and globular clusters, are much older and metal-poor, representing some of the galaxy's earliest stellar inhabitants. As we drift among the stars of Triangulum, we encounter a cosmic ecosystem of incredible diversity and complexity. Each star, from the smallest red dwarf to the most massive blue supergiant, plays its own unique role in the galaxy's ongoing evolution. Together, these stellar populations create a living galaxy that continues to grow, change, and evolve over cosmic time. Stars are the lifeblood of any galaxy, and in Triangulum, they come in every shape, size, and color. Let us drift through their varied stages of life, from birth to death, as we explore the cosmic diversity of this distant world. Our journey through the stellar menagerie of Triangulum reveals not only the incredible variety of stellar types, but also the fundamental unity of the physical processes that govern stellar evolution throughout the universe. As we continue our peaceful journey through the cosmic neighborhood of Triangulum, we encounter the smaller galaxies that orbit this magnificent spiral like faithful companions. These satellite galaxies, though modest in size compared to their host, play crucial roles in the ongoing evolution and dynamics of the Triangulum system. Each of these galactic companions tells its own story of formation, survival, and interaction within the gravitational embrace of the larger galaxy. The satellite system of Triangulum differs significantly from the rich collections of companion galaxies that surround larger spirals like the Milky Way and Andromeda. While those massive galaxies host dozens of known satellite galaxies, Triangulum's family of companions is much smaller and more intimate. This difference reflects Triangulum's smaller mass and correspondingly weaker gravitational influence, which limits its ability to capture and retain smaller galactic systems over cosmic time. Among the most notable companions of Triangulum is the irregular galaxy known as IC10, a small but active star-forming galaxy located approximately 200,000 light-years from Triangulum's center. IC10 represents one of the nearest starburst galaxies to our own local group, making it an invaluable laboratory for studying the violent processes that occur when galaxies undergo periods of intense star formation. Despite its small size, containing only about 1% the mass of Triangulum, IC10 produces new stars at a rate comparable to much larger galaxies. The relationship between IC10 and Triangulum remains a subject of ongoing astronomical investigation. Some researchers suggest that IC10 may be a true satellite galaxy, gravitationally bound to Triangulum and slowly orbiting around its larger companion. Others propose that IC10 might be an independent galaxy that happens to be passing near Triangulum during our current observational epoch. The uncertain nature of this relationship highlights the challenges astronomers face when studying the dynamics of galactic systems across cosmic distances. The stellar population of IC10 provides fascinating insights into the processes that drive star formation in small galaxies. This galaxy contains both old and young stellar populations, suggesting that it has experienced multiple episodes of star formation throughout its history. The presence of massive Wolf-Rayet stars and luminous blue variables indicates that very recent star formation has occurred, possibly triggered by gravitational interactions with Triangulum or by internal processes within the galaxy itself. Dwarf spheroidal galaxies, if they exist in Triangulum's vicinity, would represent some of the most ancient and pristine stellar systems in the local group. These faint, diffuse galaxies typically contain very old stellar populations with low heavy element abundances, making them valuable fossils of the early universe. However, detecting such faint companions around Triangulum requires extremely sensitive observations and careful analysis to distinguish genuine satellite galaxies from background objects and foreground stars. The search for satellite galaxies around Triangulum has been complicated by the galaxy's location in the sky and the limitations of current observational technology. Unlike the Milky Way, where we can conduct detailed surveys of the entire sky to search for faint companions, studying Triangulum's satellite system requires observations towards specific regions of sky where such companions might be expected to appear. This observational challenge means that our current inventory of Triangulum's satellites may be incomplete. Tidal streams, elongated trails of stars stripped from satellite galaxies by gravitational forces, provide evidence of past and ongoing interactions between Triangulum and its companions. These stellar streams can extend for hundreds of thousands of light years and remain visible for billions of years after the disruption event that created them. The detection of such streams around Triangulum would provide direct evidence of the galaxy's ability to capture and disrupt smaller stellar systems. The process of satellite galaxy accretion plays an important role in the growth and evolution of Triangulum over cosmic time. When a smaller galaxy falls into Triangulum's gravitational well, tidal forces gradually strip away its outer stars and gas, adding this material to Triangulum's halo and disk. This process, known as galactic cannibalism, allows larger galaxies to grow by consuming their smaller neighbors over billions of years. The distribution of satellite galaxies around Triangulum may provide clues about the structure of the galaxy's dark matter halo. Theoretical models predict that satellite galaxies should preferentially orbit within the dense, dark matter structures that surround their hosts. By mapping the positions and motions of Triangulum's companions, astronomers can test these predictions and learn about the invisible dark matter that dominates the galaxy's total mass. Ultra-faint dwarf galaxies, if they exist around Triangulum, would represent some of the most dark matter-dominated objects in the universe. These extremely low luminosity systems contain only a few thousand stars, but may harbor dark matter halos with masses millions of times greater than their stellar content. The detection of such objects around Triangulum would provide important tests of our understanding of galaxy formation in the smallest dark matter halos. The chemical composition of satellite galaxies often differs significantly from that of their host galaxy, reflecting their independent evolutionary histories before being captured by the larger system. These chemical differences can persist for billions of years after capture, allowing astronomers to use stellar chemistry as a tool for identifying stars that originated in disrupted satellite galaxies. Such chemical tagging has revealed evidence of ancient merger events in the formation histories of many large galaxies. Star formation histories in Triangulum satellite galaxies are likely to be episodic and influenced by their interactions with the host galaxy. As a satellite galaxy orbits through Triangulum's halo, it experiences varying gravitational forces and encounters with gas and dust that can trigger bursts of star formation. These interaction-driven starbursts can temporarily increase the satellite's luminosity and alter its stellar population characteristics. The survival of satellite galaxies in Triangulum's gravitational field depends on several factors, including their initial mass, density profile, and orbital characteristics. More massive and compact satellites are better able to resist tidal disruption and maintain their structural integrity over long periods. Satellites on highly elliptical orbits experience stronger tidal forces during their closest approaches to Triangulum, making them more susceptible to disruption than those on circular orbits. Gas stripping represents another important process affecting satellite galaxies in the Triangulum system. As satellites move through the hot gas that surrounds Triangulum, ram pressure forces can strip away their interstellar medium, effectively terminating star formation and transforming gas-rich spiral or irregular galaxies into gas-poor spheroidal systems. This process helps explain why many satellite galaxies appear to be dominated by old stellar populations. The globular cluster systems of Triangulum's satellites provide additional windows into their formation and evolution histories. Some satellite galaxies host their own collections of globular clusters, ancient stellar systems that formed during the galaxy's early epochs. When satellites are disrupted by tidal forces, their globular clusters can be scattered throughout Triangulum's halo, where they continue to orbit as independent objects. Stellar kinematics within satellite galaxies can reveal the presence and distribution of dark matter in these systems. By measuring the velocities of individual stars or stellar populations within a satellite galaxy, astronomers can infer the total mass distribution and determine how much dark matter is required to explain the observed motions. These measurements provide crucial tests of dark matter theories and galaxy formation models. The future evolution of Triangulum's satellite system will be shaped by continued gravitational interactions and the gradual merger of smaller companions with the host galaxy. Over cosmic time, most satellite galaxies will either be disrupted by tidal forces or will spiral inward and merge directly with Triangulum's main body. This ongoing process of satellite accretion will continue to add mass and complexity to Triangulum's structure. The study of satellite galaxies around Triangulum also provides important context for understanding the broader evolution of the local group. The interactions between Triangulum and its companions occur within the larger gravitational framework established by the Milky Way and Andromeda galaxies. As the local group evolves over cosmic time, the changing gravitational environment will influence the dynamics of satellite systems around all member galaxies. Environmental effects may have suppressed the formation or survival of satellite galaxies around Triangulum compared to more isolated spiral galaxies. The presence of the much more massive Andromeda and Milky Way galaxies in the local group creates tidal forces that can strip satellites from smaller galaxies or prevent them from capturing new companions. This environmental influence may explain why Triangulum appears to have fewer satellite galaxies than might be expected based on its mass alone. The detection and study of satellite galaxies around Triangulum requires sophisticated observational techniques and careful data analysis. Modern wide field surveys and deep imaging capabilities have greatly improved our ability to detect faint stellar systems in the outer regions of nearby galaxies. These technological advances continue to reveal new satellite galaxies and provide better understanding of their properties and distributions. Machine learning and automated detection algorithms are increasingly being used to identify candidate satellite galaxies in large astronomical data sets. These computational tools can efficiently search through millions of astronomical objects to identify the subtle signatures of resolved stellar populations that characterize genuine satellite galaxies. Such techniques will be essential for conducting comprehensive surveys of Triangulum's satellite system in the coming years. The comparison between Triangulum's satellite system and those of other local group galaxies provides valuable insights into how galaxy mass, environment, and evolutionary history influence the formation and retention of companion galaxies. These comparative studies help astronomers understand the fundamental processes that shape galactic systems and test theoretical models of structure formation in the universe. As we journey through the extended region around Triangulum, we encounter these smaller companions that add richness and complexity to the galactic environment. Each satellite galaxy, whether it be the active star-forming region of IC10 or the hypothetical ultra-faint dwarfs that may lurk in the outer reaches of Triangulum's halo, contributes to our understanding of how galaxies form, evolve, and interact over cosmic time. Triangulum is not an island unto itself. It has companions, smaller galaxies that orbit and interact with it. Together, they form a complex, interconnected family, each galaxy playing its role in the cosmic dance. Our exploration of these satellite systems reveals the intricate web of gravitational relationships that bind galactic communities together and shape their evolution across billions of years of cosmic history. As we continue our tranquil voyage through the Triangulum galaxy, we now turn our attention to one of the most profound mysteries in modern astronomy, the invisible dark matter that surrounds and permeates this cosmic island. Though we cannot see it directly, dark matter represents the dominant component of Triangulum's total mass, providing the gravitational scaffolding upon which the visible galaxy has been constructed. This invisible realm challenges our understanding of the universe while simultaneously revealing the elegant hidden architecture that shapes galactic evolution. The story of dark matter's discovery began in the 1930s, when astronomer Fritz Zwicky observed that galaxies in distant clusters were moving too fast to be held together by the gravity of their visible matter alone. However, it was not until the 1970s that astronomers Vera Rubin and Kent Ford provided compelling evidence for dark matter in individual galaxies by studying their rotation curves. Their observations of spiral galaxies, including systems similar to Triangulum, showed that stars in the outer regions were orbiting much faster than predicted by the visible matter alone. In Triangulum, as in other spiral galaxies, the rotation curve provides the clearest evidence for the presence of dark matter. If the galaxy contained only the visible stars, gas, and dust that we can observe directly, stars in the outer regions should orbit much more slowly than those closer to the center, following the same pattern that governs planetary motion in our solar system. Instead, observations reveal that the orbital velocities of stars and gas clouds remain roughly constant even at large distances from the galactic center. indicating the presence of additional invisible mass. This flat rotation curve extends far beyond the visible edges of Triangulum's stellar disk, suggesting that the galaxy is embedded within a much larger halo of dark matter. Computer simulations and theoretical models indicate that this dark matter halo may extend to distances of several 100,000 light-years from the galactic center, making it many times larger than the visible galaxy itself. The total mass of dark matter in Triangulum likely exceeds the mass of all visible matter by a factor of 5 to 10. The nature of dark matter remains one of the greatest unsolved puzzles in physics and astronomy. Unlike ordinary matter, which interacts electromagnetically and can absorb, emit, or scatter light, dark matter appears to interact only through gravitational forces. This makes it effectively invisible to all forms of electromagnetic radiation, from radio waves to gamma rays. Scientists can detect dark matter's presence only through its gravitational effects on visible matter and the large-scale structure of the universe. Current theories propose that dark matter consists of exotic particles that were created in the early universe but have no counterparts among the known particles of the standard model of physics. These hypothetical particles, with names like WIMPs, weakly interacting massive particles, and axions, would have been produced in the hot, dense conditions that existed shortly after the Big Bang. As the universe expanded and cooled, these particles would have clumped together under their own gravity, forming the dark matter halos that host galaxies today. The distribution of dark matter within Triangulum's halo follows a predictable pattern that emerges from computer simulations of cosmic structure formation. Near the galactic center, the dark matter density is relatively high, providing the deep gravitational well necessary to bind the central stellar population together. As we move outward from the center, the dark matter density gradually decreases, but the total amount of dark matter continues to increase due to the larger volume of space contained within each successive spherical shell. This dark matter distribution creates what astronomers call a cuspy halo profile, where the density increases steeply toward the galactic center. However, observations of some galaxies, including dwarf galaxies that may be satellites of Triangulum, suggest that the actual dark matter distribution might be less centrally concentrated than predicted by simulations. This discrepancy, known as the core cusp problem, represents one of several small-scale challenges facing our current understanding of dark matter. The formation of Triangulum's dark matter halo began in the early universe, when tiny fluctuations in the cosmic matter distribution were amplified by gravitational attraction. These initial density variations, imprinted during the cosmic inflation that occurred in the first fraction of a second after the Big Bang, served as seeds for all subsequent structure formation. Over billions of years, dark matter particles slowly accumulated in regions of slightly higher than average density, eventually forming the massive halos that host galaxies today. The process of halo formation occurred hierarchically, with smaller dark matter clumps merging to form progressively larger structures. Triangulum's halo likely formed through the merger of many smaller dark matter halos over cosmic time, gradually building up the mass and complexity we observe today. This hierarchical assembly process continues even now, as Triangulum's halo slowly accretes additional dark matter from its cosmic environment and occasionally captures smaller dark matter subhalos. Within Triangulum's dark matter halo, computer simulations predict the existence of numerous dark matter subhalos, smaller concentrations of dark matter that survived the galaxy formation process. These subhalos, which may number in the thousands within Triangulum's halo, could potentially host their own small populations of stars if they were massive enough to retain gas during the early epochs of cosmic evolution. The search for these predicted subhalos represents an important test of our understanding of dark matter and galaxy formation. The interaction between dark matter and ordinary matter in Triangulum occurs primarily through gravitational forces, but this interaction has profoundly shaped the galaxy's evolution. The deep gravitational well created by the dark matter halo provided the necessary conditions for gas to cool and condense, eventually forming the first stars and beginning the process of galaxy formation. Without dark matter, the ordinary matter in the universe would never have been able to overcome the cosmic expansion and collapse into the structures we observe today. The dark matter halo also plays a crucial role in regulating star formation within Triangulum. The halo's gravitational field helps confine gas within the galactic disk, preventing it from escaping into intergalactic space and ensuring a steady supply of raw material for continued star formation. At the same time, the halo's influence on the galaxy's rotation curve affects the stability of spiral density waves, helping to maintain the beautiful spiral arm structure we observe. Gravitational lensing provides another tool for studying dark matter in and around Triangulum. When light from more distant galaxies passes near Triangulum, the gravitational field of its dark matter halo can bend and distort the light rays, creating subtle changes in the apparent shapes and positions of background objects. While these effects are typically too small to detect with current technology, for a galaxy at Triangulum's distance, future observations may be sensitive enough to directly map the dark matter distribution through its lensing signature. The search for dark matter particles themselves continues in laboratories around the world, using sophisticated detectors designed to catch the extremely rare interactions between dark matter particles and ordinary matter. Underground experiments shield sensitive detectors from cosmic rays and other background radiation, hoping to detect the tiny energy deposits that would result if a dark matter particle collided with an atomic nucleus. So far, these searches have not definitively detected dark matter particles, but they continue to place increasingly stringent limits on the properties these particles must have. Particle accelerators like the Large Hadron Collider also search for dark matter by attempting to create dark matter particles in high-energy collisions between protons. If dark matter particles can be produced in these collisions, they would immediately escape the detector without leaving a direct trace, but their presence could be inferred from the missing energy and momentum in the collision products. These searches complement the direct detection experiments and provide additional constraints on dark matter theories. Alternative theories of gravity, such as modified Newtonian dynamics or MOND, attempt to explain the observed rotation curves of galaxies, like Triangulum, without invoking dark matter. These theories propose that the laws of gravity behave differently on galactic scales than predicted by Einstein's general relativity, producing the observed flat rotation curves through modifications to gravitational physics rather than through the presence of invisible matter. While these theories can explain some galactic observations, they struggle to account for other evidence for dark matter on larger cosmic scales. The cosmic microwave background radiation, the afterglow of the Big Bang, provides strong evidence for the existence of dark matter on the largest scales. The pattern of tiny temperature fluctuations in this ancient light reveals the distribution of matter in the early universe and requires the presence of dark matter to match observations. The precise agreement between theoretical predictions that include dark matter and the observed cosmic microwave background patterns represents one of the strongest pieces of evidence for the dark matter paradigm. Computer simulations of cosmic structure formation, which follow the evolution of both dark matter and ordinary matter from the early universe to the present day, successfully reproduce many observed properties of galaxies like Triangulum when dark matter is included. These simulations predict the formation of galactic halos with the correct masses, sizes, and internal structures to match observations. They also successfully predict the large-scale distribution of galaxies throughout the universe, providing additional support for dark matter theories. The interaction between dark matter and the baryonic ordinary matter in Triangulum occurs through complex feedback processes that are still not fully understood. Supernova explosions and stellar winds can drive gas out of the galactic disk, potentially affecting the distribution of both ordinary and dark matter within the galaxy. These feedback processes may help explain some of the discrepancies between theoretical predictions and observations of dark matter distributions in galaxies. Future space-based telescopes and ground-based observatories will provide new opportunities to study dark matter in Triangulum and other nearby galaxies. Advanced imaging capabilities will allow astronomers to map stellar motions with unprecedented precision, providing better constraints on the dark matter distribution. Wide-field surveys will also help identify more satellite galaxies and stellar streams that can serve as probes of the dark matter halo's gravitational field. The study of dark matter in Triangulum contributes to our broader understanding of cosmic evolution and the fundamental nature of the universe. Dark matter appears to be essential for explaining how galaxies formed and evolved over cosmic time, yet its true nature remains mysterious. The continued investigation of dark matter in nearby galaxies like Triangulum may eventually lead to breakthrough discoveries that revolutionize our understanding of physics and cosmology. As we contemplate the invisible realm of dark matter that surrounds Triangulum, we encounter one of the most humbling aspects of modern astronomy. The universe is dominated by forms of matter and energy that we cannot directly observe, reminding us that our current understanding of cosmic reality is far from complete. The dark matter halo of Triangulum, though invisible to our eyes, represents a fundamental component of galactic architecture that has shaped the formation and evolution of every cosmic structure we observe. Beyond the glowing stars and nebulae, there is an invisible force at work. Dark matter, which we cannot see, binds the galaxy together. It is the unseen hand shaping the universe, providing the gravitational foundation upon which the cosmic structures we observe have been built. Our journey through Triangulum's dark matter halo reveals the profound mysteries that still challenge our understanding of the cosmos and inspire continued exploration of the invisible universe that surrounds us. As we continue our peaceful journey through Triangulum, we now turn our gaze toward the distant future, contemplating the cosmic destiny that awaits this magnificent galaxy. The story of Triangulum's future is intimately connected to the gravitational dance of the local group, a slow-motion ballet that will unfold over billions of years. Through careful observation and sophisticated computer modeling, astronomers have begun to glimpse the extraordinary transformations that await Triangulum and its galactic neighbors in the deep future of cosmic time. The future of Triangulum cannot be understood in isolation, for this galaxy exists within the gravitational embrace of the local group, our cosmic neighborhood that contains more than 50 galaxies bound together by their mutual gravitational attraction. The three largest members of this group, the Andromeda Galaxy, our own Milky Way, and Triangulum itself, dominate the gravitational dynamics and will ultimately determine the fate of all smaller galaxies in the region. Current observations reveal that the Andromeda Galaxy is approaching our Milky Way at a velocity of approximately 110 kilometers per second. This cosmic collision, predicted to occur in roughly 4.5 billion years, will fundamentally reshape the local group and create entirely new galactic structures. The merger of these two massive spiral galaxies will produce what astronomers have dubbed Milkomeda, a giant elliptical galaxy that will become the new gravitational center of our cosmic neighborhood. The role that Triangulum will play in this cosmic collision remains one of the most intriguing questions in galactic astronomy. Computer simulations suggest several possible scenarios for Triangulum's fate, each depending on the precise details of its current motion and the complex gravitational interactions that will occur during the Milky Way-Andromeda merger. These simulations must account for the three-dimensional positions and velocities of all the major galaxies, as well as the influence of dark matter halos that extend far beyond the visible boundaries of each galaxy. One possibility is that Triangulum will be drawn into the collision between the Milky Way and Andromeda, creating a spectacular three-way galactic merger. In this scenario, Triangulum would approach the merging system during or shortly after the initial collision, adding its own stars, gas, and dark matter to the cosmic maelstrom. The resulting galaxy would be even more massive than the simple Milky Way Andromeda merger, potentially creating one of the most massive elliptical galaxies in the local universe. Alternatively, Triangulum might avoid direct participation in the main collision, instead orbiting the newly formed Milky galaxy as a large satellite. This outcome would depend on Triangulum's precise trajectory and velocity relative to the merging galaxies. If Triangulum passes near but not through the merger region, it could be captured into a stable orbit around the combined system, similar to how the large and small Magellanic Clouds currently orbit our Milky Way. A third possibility is that Triangulum could be ejected from the local group entirely during the chaotic gravitational interactions of the merger. The violent redistribution of mass during galactic collisions can impart large velocities to nearby objects, potentially flinging smaller galaxies into the intergalactic void. If this occurs, Triangulum would become an isolated galaxy, slowly drifting through the empty space between galaxy clusters with little hope of future interactions with other large stellar systems. The timeline for these cosmic events unfolds over scales that dwarf human experience, and even the entire history of life on Earth. The Milky Way Andromeda collision will begin in approximately 4.5 billion years, roughly the same amount of time that has elapsed since the formation of our solar system. The actual merger process will then take place over several billion additional years as the two galaxies experience multiple close encounters before finally settling into a single, stable configuration. During the merger process, the spiral structures of both the Milky Way and Andromeda will be completely disrupted by gravitational forces. The beautiful spiral arms that currently define these galaxies will be stretched, twisted, and eventually destroyed as the galactic disks are scrambled by tidal interactions. The resulting galaxy will likely be a giant elliptical system, dominated by stars following chaotic orbits rather than the organized rotation that characterizes spiral galaxies. For Triangulum, the disruption of spiral structure would mark the end of its current epoch of active star formation. The galaxy's spiral density waves, which currently trigger star formation by compressing gas clouds, would be destroyed by the gravitational chaos of the merger. Without these organizing structures, star formation would likely cease, except in regions where direct collisions between gas clouds provide the necessary compression for gravitational collapse. The stellar populations of Triangulum would be profoundly affected by a merger with the Milky Way and Andromeda. Stars that currently reside in the galaxy's disk would be scattered throughout a much larger volume of space, with some being ejected entirely from the combined system. The dense stellar environment near the center of the merged galaxy would lead to increased rates of stellar encounters and collisions, potentially creating exotic objects like blue straggler stars and millisecond pulsars. The supermassive black holes at the centers of the merging galaxies would also undergo dramatic changes during the collision. If Triangulum possesses a central black hole, as most galaxies do, it would eventually spiral toward the center of the merged system along with the black holes from the Milky Way and Andromeda. The final coalescence of these massive objects would produce gravitational waves of enormous amplitude, rippling through space-time itself as the black holes merge into a single, even more massive object. Gas dynamics during the merger would create spectacular displays of star formation as shockwaves and compression fronts trigger the collapse of molecular clouds throughout the interacting galaxies. These collision-induced starbursts could temporarily increase the rate of star formation by factors of 10 or more, creating brilliant regions of blue giant stars and associated nebulae. However, this enhanced star formation would be followed by a long quiescent period as the available gas supply becomes exhausted. The globular cluster systems of the merging galaxies would also be affected by the collision. Some clusters would be stripped from their parent galaxies by tidal forces and scattered throughout the merged system. Others might be destroyed entirely if they pass too close to the galactic centers during the merger. The surviving clusters would provide important fossil records of the pre-merger galaxies, preserving information about their stellar populations and formation histories. Dark matter dynamics during galactic mergers follow different patterns than the behavior of ordinary matter. While stars and gas can experience shock waves and collisional interactions, dark matter particles interact only gravitationally and pass through each other without direct collisions. This difference leads to complex redistributions of matter during mergers, with dark matter halos typically responding more slowly to the collision than the visible components of the galaxies. The effects of the merger on planetary systems within Triangulum and the other galaxies would be minimal for most stars. Despite the dramatic disruption of galactic structure, the vast distances between individual stars mean that direct stellar encounters would remain extremely rare. Most planetary systems would simply find themselves in new galactic environments, orbiting stars that follow different trajectories through a larger and more chaotic stellar system. Computer simulations of local group evolution must account for the influence of dark energy, the mysterious force that drives the accelerating expansion of the universe. This cosmic acceleration works against gravitational attraction on the largest scales, potentially affecting the long-term dynamics of galaxy groups and clusters. However, within the local group, gravitational forces are strong enough to overcome dark energy, allowing the planned merger to proceed despite the overall expansion of space. The far future evolution of the merged galaxy system will be influenced by the gradual evaporation of stellar orbits through a process called gravitational relaxation. Over timescales of trillions of years, stellar encounters will gradually alter the orbits of stars within the galaxy, causing some to migrate toward the galactic center, while others are ejected into intergalactic space. This process will slowly disperse the merged galaxy, though it will take much longer than the current age of the universe to significantly alter the system's structure. Observational astronomy provides several methods for constraining the future evolution of Triangulum and the local group. Precise measurements of stellar positions and velocities using space-based telescopes like Gaia allow astronomers to determine the three-dimensional motions of nearby galaxies with unprecedented accuracy. These observations provide the initial conditions necessary for running detailed computer simulations of future galactic evolution. The study of galaxy mergers in other parts of the universe provides important insights into the processes that will affect Triangulum in the future. Astronomers can observe galaxies at various stages of collision and merger, from initial approach through final coalescence, providing a comprehensive picture of how these cosmic events unfold. These observations help calibrate computer simulations and test our understanding of galactic dynamics. Advanced gravitational wave detectors may eventually be sensitive enough to detect the mergers of supermassive black holes that occur during galactic collisions. The detection of such events would provide direct confirmation of theoretical predictions about galactic mergers and offer new insights into the behavior of matter and space-time under extreme gravitational conditions. The ultimate fate of Triangulum depends not only on its interactions with other local group galaxies, but also on the fundamental properties of the universe itself. If dark energy continues to dominate cosmic evolution, the local group will become increasingly isolated from other galaxy clusters as the expansion of space carries them beyond the reach of gravitational interaction. In this scenario, the merged galaxy system would represent a cosmic island, slowly evolving in isolation as the universe around it becomes increasingly empty and cold. Alternative cosmological models, such as those involving phantom dark energy or cyclic universes, could lead to very different fates for Triangulum and other galaxies. Some theories predict that the acceleration of cosmic expansion could eventually overcome even the gravitational binding of individual galaxies, leading to a Big Rip scenario where all bound structures are torn apart. Other models suggest that the universe might eventually collapse in a big crunch, bringing all galaxies back together in a reversal of the Big Bang. As we contemplate these vast timescales and cosmic transformations, we gain perspective on our own place in the universe and the temporary nature of all cosmic structures. The beautiful spiral galaxy we observe today represents just one phase in Triangulum's long evolutionary history, and the future holds changes that will be just as dramatic as those that have already occurred during the galaxy's billions of years of existence. The prediction of Triangulum's future collision with other local group galaxies reminds us that the universe is dynamic and ever-changing. Nothing in the cosmos is permanent, from the shortest-lived massive stars to the largest galactic structures. This cosmic impermanence, rather than being cause for melancholy, highlights the preciousness of the present moment and the remarkable privilege of being able to observe and understand the universe during this particular epoch of cosmic history. The future of Triangulum is uncertain as it moves slowly toward a potential collision with our own galaxy. But in the slow rhythm of cosmic collisions, there is rebirth. Perhaps in the distant future, Triangulum will be reshaped into something entirely new, contributing its stars and stories to a galaxy unlike any we have seen before. The cosmic dance continues, and we are fortunate witnesses to its eternal choreography. As our peaceful journey through the Triangulum galaxy draws toward its conclusion, we turn our thoughts to the future of human exploration and understanding of this distant cosmic realm. While Triangulum remains far beyond the reach of current technology, lying nearly 3 million light-years from Earth, the rapid advancement of astronomical instruments and techniques continues to bring this magnificent galaxy closer to our comprehension. The future holds remarkable possibilities for deepening our knowledge of Triangulum and perhaps even discovering signs of life within its billions of stars. The next generation of ground-based telescopes promises to revolutionize our view of Triangulum and other nearby galaxies. The extremely large telescope, with its primary mirror spanning 39 meters in diameter, will possess the light-gathering power to resolve individual stars within Triangulum's spiral arms. This unprecedented capability will allow astronomers to study stellar populations, measure their chemical compositions, and track their motions with precision previously reserved for stars within our own galaxy. Advanced adaptive optic systems will work in concert with these giant telescopes to correct for the blurring effects of Earth's atmosphere. These sophisticated technologies use deformable mirrors that change shape hundreds of times per second to compensate for atmospheric turbulence, effectively creating space-like observing conditions from the ground. With such systems, astronomers will be able to peer deep into Triangulum's spiral arms and study the detailed structure of its star-forming regions. Space-based observatories represent another frontier in Triangulum exploration. The James Webb Space Telescope has already begun to transform our understanding of distant galaxies, and future missions will build upon these capabilities. The proposed Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, would dwarf even the James Webb Telescope in size and capability, potentially allowing direct imaging of Earth-like planets around nearby stars within Triangulum. Gravitational wave astronomy opens entirely new windows for studying Triangulum and other distant galaxies. As black hole mergers and neutron-star collisions occur within Triangulum, they generate ripples in space-time that travel across the universe at the speed of light. Future gravitational wave detectors, both on Earth and in space, will be sensitive enough to detect these cosmic events and provide information about the most extreme objects within Triangulum's stellar population. The search for extraterrestrial intelligence may eventually extend to Triangulum itself. While the enormous distances involved make direct communication impossible on human timescales, astronomers might one day detect artificial signals originating from technological civilizations within this distant galaxy. The development of more sensitive radio telescopes and signal processing techniques could reveal evidence of intelligence among Triangulum's billions of stars. Robotic interstellar missions, though still in the realm of speculation, could theoretically reach Triangulum given sufficient technological advancement and time. Breakthrough Starshot and similar initiatives are exploring the possibility of using light sails propelled by powerful laser arrays to achieve significant fractions of the speed of light. While reaching Triangulum would require journey times of millions of years even at these velocities, such missions could provide unprecedented close-up views of this distant galaxy. The development of artificial intelligence and machine learning will play crucial roles in future Triangulum research. The vast amounts of data collected by next-generation telescopes will require sophisticated algorithms to identify interesting objects and phenomena within the galaxy. AI systems will be capable of automatically detecting supernovae, variable stars, and potentially even signs of technological activity among Triangulum's stellar population. Quantum sensing technologies may provide new tools for studying the dark matter that surrounds Triangulum. Ultra-sensitive quantum interferometers and atomic clocks could potentially detect the subtle effects of dark matter particles passing through our solar system. Such detections would provide direct confirmation of dark matter's existence and help constrain the properties of the particles that make up Triangulum's invisible halo. The concept of generation ships, massive spacecraft designed to sustain human populations for thousands of years, represents the most speculative yet inspiring possibility for Triangulum exploration. Such vessels would need to be entirely self-sufficient ecosystems, capable of maintaining complex technological civilizations across the vast journey between galaxies. While such projects remain far beyond current capabilities, they capture the human imagination and drive for exploration. Virtual reality and augmented reality technologies will allow future generations to experience Triangulum in ways that we can barely imagine today. Advanced computer simulations based on detailed observational data could create immersive environments where people can explore Triangulum's spiral arms, visit its star-forming regions, and witness the birth and death of stars. These virtual journeys would make the galaxy accessible to millions of people who could never physically travel there. The study of extremophile organisms on Earth provides insights into the types of life that might exist within Triangulum's diverse stellar environments. Organisms that thrive in extreme heat, cold, radiation, and chemical conditions expand our understanding of life's possibilities and inform the search for biological activity around Triangulum's stars. Future missions to Triangulum might specifically target environments that could support such hardy forms of life. Advanced propulsion technologies, such as fusion rockets, antimatter engines, or even theoretical concepts like Alcubierre drives, could dramatically reduce travel times to Triangulum. While these technologies remain largely theoretical, continued research in fundamental physics might eventually make interstellar and even intergalactic travel practical. The development of such capabilities would transform humanity into a truly cosmic civilization. The preservation of Triangulum's beauty and scientific value will become increasingly important as our technological capabilities advance. Just as we protect pristine environments on Earth, future spacefaring civilizations may need to establish protocols for respectful exploration of distant galaxies. The pristine nature of Triangulum's stellar populations and interstellar medium makes it an invaluable laboratory for understanding galactic evolution. Citizen science initiatives will play expanding roles in Triangulum research as data becomes more accessible and analysis tools more sophisticated. Amateur astronomers and volunteers around the world already contribute to galaxy classification projects and supernova searches. Future platforms will allow even broader participation in analyzing the wealth of data collected by next-generation telescopes. The economic drivers for Triangulum exploration may emerge from unexpected directions. While the galaxy contains no accessible resources for human use, the technologies developed for studying and potentially reaching Triangulum could have transformative applications closer to home. Advanced propulsion systems, life support technologies, and AI systems developed for galactic exploration could revolutionize space travel within our own solar system. Educational opportunities surrounding Triangulum exploration will inspire future generations of scientists, engineers, and explorers. The galaxy's beauty and mystery make it an ideal subject for capturing young imaginations and motivating careers in science and technology. Virtual field trips to Triangulum, interactive simulations of stellar evolution, and hands-on analysis of astronomical data will bring the excitement of cosmic discovery into classrooms around the world. International cooperation will be essential for ambitious Triangulum research projects. The enormous costs and technical challenges involved in studying distant galaxies will require collaboration between nations and organizations on an unprecedented scale. These partnerships will not only advance our scientific understanding, but also promote peaceful cooperation and shared purpose among Earth's diverse cultures. The philosophical implications of Triangulum exploration extend far beyond scientific discovery. As we develop the capability to study this galaxy in ever greater detail, we gain perspective on our own place in the cosmic hierarchy. Triangulum reminds us that our galaxy is just one among billions, each containing its own stories of stellar birth, evolution, and death. The timeline for major advances in Triangulum exploration will likely span multiple human generations. While some technological breakthroughs may occur rapidly, the fundamental challenges of studying objects at such vast distances ensure that progress will be gradual and cumulative. This long-term perspective requires sustained commitment to scientific research and education across many decades. As we consider the ethical dimensions of future Triangulum exploration, we must grapple with questions about our responsibilities toward potentially existing life within this distant galaxy. How should humanity proceed if we detect signs of intelligence among Triangulum's stars? What protocols should govern our attempts to communicate across such vast distances? These questions will become increasingly relevant as our detection capabilities improve. The potential for unexpected discoveries within Triangulum remains one of the most exciting aspects of future exploration. History shows that our most profound scientific breakthroughs often come from observations that reveal phenomena we never anticipated. Triangulum may harbor stellar objects, physical processes, or even forms of organization that challenge our current understanding of the universe. The legacy of Triangulum exploration will extend far beyond the scientific knowledge gained from studying this distant galaxy. The technologies, methodologies, and international partnerships developed for this research will establish frameworks for exploring even more distant cosmic structures. Triangulum serves as a stepping stone toward understanding the broader universe and humanity's place within it. As we dream of future exploration and discovery, we recognize that each technological advance brings us closer to answering fundamental questions about the nature of galaxies, stars, and potentially life itself. The journey toward understanding Triangulum represents more than scientific curiosity. It embodies humanity's deepest aspirations to explore, discover, and comprehend our cosmic home. While we are distant from Triangulum, the dream of exploring it, of understanding its stars, planets, and mysteries, is one that may come true one day. As technology advances, so too does our ability to unlock the secrets of the cosmos. Our future relationship with Triangulum will be shaped by our technological capabilities, our scientific curiosity, and our collective commitment to exploring the wonders that await us among the stars. As our gentle voyage through the Triangulum galaxy comes to its peaceful conclusion, we find ourselves profoundly changed by the cosmic journey we have shared. We have drifted through spiral arms alive with stellar birth, contemplated the ancient wisdom held within the galactic core, and marveled at the invisible dark matter that binds this magnificent galaxy together. Through our exploration of Triangulum, we have touched something infinite and eternal, a reminder that we are part of a universe far grander and more beautiful than our daily lives often allow us to remember. The Triangulum galaxy, suspended in the cosmic deep nearly 3 million light-years from our earthly home, has revealed itself to us as more than a distant collection of stars and gas. It has shown us the fundamental processes that govern all cosmic evolution, from the collapse of molecular clouds that births new stars, to the patient dance of gravity that maintains galactic structure across billions of years. In studying Triangulum, we have studied ourselves, for the same physical laws that shape this distant galaxy also govern the atoms in our bodies and the planet beneath our feet. Throughout our journey, we have witnessed the endless cycle of creation and destruction that defines cosmic evolution. Stars are born in the cold depths of molecular clouds, live out their nuclear-burning lifetimes, and return their enriched material to the interstellar medium through stellar winds and explosive deaths. This cosmic recycling ensures that each new generation of stars is more chemically complex than the last, gradually building the heavy elements necessary for rocky planets and the chemistry of life itself. The beauty we have encountered in Triangulum transcends mere visual spectacle, though the galaxy's spiral arms and glowing nebulae certainly rank among the most magnificent sights in the universe. The deeper beauty lies in the elegant physical processes that create and maintain these structures, in the delicate balance between gravity and nuclear fire that allows stars to shine for billions of years, and in the cosmic choreography that keeps galaxies stable while allowing them to evolve and change over cosmic time. Our exploration has revealed Triangulum as a living system, not a static collection of celestial objects, but a dynamic, evolving entity that responds to internal processes and external influences. The galaxy breathes with cycles of star formation and stellar death, its spiral arms serving as cosmic assembly lines that transform raw hydrogen into the complex chemistry of stellar atmospheres and planetary surfaces. This vitality reminds us that the universe itself is alive with change and possibility. The mysteries we have encountered in Triangulum, from the nature of dark matter to the potential for life among its billions of stars, humble us with their complexity while inspiring us to continue seeking understanding. The universe does not yield its secrets easily, but each question answered reveals new depths of wonder and complexity. Our incomplete knowledge serves not as a limitation, but as an invitation to continue exploring, learning, and growing in our cosmic perspective. The scale of Triangulum challenges our earthbound intuitions about space and time. The galaxy spans 60,000 light-years and contains tens of billions of stars, numbers that stretch our comprehension to its limits. Yet this immensity also offers comfort, reminding us that we exist within a universe of extraordinary richness and possibility. No matter how vast our problems may seem from our human perspective, they exist within a cosmic context that puts all earthly concerns into perspective. The temporal scales we have contemplated during our journey through Triangulum offer their own form of peace and understanding. The galaxy has been evolving for over 10 billion years, and its future extends for billions more years into the cosmic future. This deep time perspective reminds us that patience is built into the very fabric of the universe. Change occurs slowly but inevitably, and the most beautiful cosmic structures arise from the gradual accumulation of countless small processes over vast periods of time. Our encounter with Triangulum's stellar populations has introduced us to the diversity of cosmic environments and the many pathways that stellar evolution can follow. From the patient red dwarf stars that will outlive the galaxy itself to the spectacular blue giants that burn brilliantly for just a few million years. we have seen that the universe supports an incredible variety of stellar types and evolutionary paths. This diversity suggests that cosmic creativity knows no bounds, and that the universe delights in exploring every possible avenue of development. The dark matter that permeates Triangulum has reminded us that the universe holds mysteries that may forever elude direct observation, yet profoundly influence everything we can see. This invisible component of cosmic reality teaches us humility about the limits of human perception, while inspiring us to develop ever more ingenious methods for studying the universe. The existence of dark matter suggests that reality extends far beyond what our senses can directly apprehend. The future evolution of Triangulum, including its potential collision with other local group galaxies, has shown us that even the largest cosmic structures are temporary and subject to change. This impermanence, rather than being cause for sadness, highlights the preciousness of the present moment and the privilege of being able to observe the universe during this particular epoch of cosmic history. We are witnessing Triangulum during its spiral galaxy phase, a beautiful chapter in its long evolutionary story. Our exploration of the satellite galaxies and the complex gravitational relationships within the local group has revealed that no galaxy is truly isolated. Cosmic evolution proceeds through interactions and relationships, with galaxies influencing each other across vast distances and over enormous timescales. This interconnectedness reflects a fundamental property of the universe, where everything influences everything else through the patient action of gravitational forces. The scientific methods and technologies that have allowed us to study Triangulum represent humanity's greatest achievements in understanding the cosmos. From the theoretical framework of stellar evolution to the observational techniques that reveal galactic structure, our knowledge of Triangulum represents the culmination of centuries of scientific progress. This accumulated wisdom stands as a testament to human curiosity and our species' remarkable capacity for understanding the universe. As we contemplate the possibility of future exploration of Triangulum, whether through advanced telescopes, robotic probes, or even speculative human missions, we are reminded that the universe offers endless opportunities for discovery and exploration. Though the galaxy remains far beyond our current reach, the trajectory of technological development suggests that our descendants may one day explore Triangulum as intimately as we now study nearby stars and planets. The peace we have found in our journey through Triangulum comes not from escape from reality, but from a deeper engagement with cosmic truth. By placing ourselves within the vast context of galactic evolution, we gain perspective on our own lives and challenges. The problems that loom large in our daily experience become more manageable when viewed against the backdrop of cosmic time and space. The wonder we have experienced in exploring Triangulum reflects an essential human capacity for awe and curiosity about the natural world. This sense of wonder is not mere entertainment, but a fundamental aspect of human consciousness that connects us to the cosmos and drives our continued growth in knowledge and understanding. By nurturing this wonder, we remain open to the transformative power of cosmic discovery. As we prepare to rest beneath the stars and allow the gentle rhythms of the universe to carry us into peaceful sleep, we carry with us the memory of our journey through Triangulum. This distant galaxy has shared its secrets with us, revealing the fundamental processes that shape all cosmic evolution. We have learned that we are made of star stuff, that the elements in our bodies were forged in stellar cores similar to those still burning in Triangulum's spiral arms. The silence we encounter at the end of our cosmic journey is not empty, but full of possibility. It is the silence of vast spaces between stars, the quiet of molecular clouds where new stars are waiting to be born, and the peaceful rhythm of galactic rotation that has continued unchanged for billions of years. This cosmic silence invites us to rest, to contemplate, and to dream of the infinite possibilities that await discovery in the universe around us. Triangulum, a galaxy of stars, nebulae, and secrets, is just one of countless galaxies in the vast universe. As we rest beneath the stars, we embrace the infinite mysteries that lie beyond our reach, knowing that each discovery brings us closer to understanding the beauty of the cosmos. The journey through Triangulum ends, but the cosmic journey continues forever, in our dreams, in our imagination, and in the endless dance of matter and energy that fills the universe with light, life, and wonder. In the gentle glow of starlight, in the patient turning of galaxies, and in the quiet majesty of cosmic evolution, we find our rest and our inspiration. The universe awaits, vast and beautiful, ready to share its secrets with those who take the time to listen to the whispered stories told by light that has traveled for millions of years to reach our wondering eyes.